go over section 1.5, which is the concept of properties of limits. When working with limits, there are some properties that will enable us to solve limit problems easier. So we will go over these properties one by one by showing examples, which some of them we actually already encountered with previous problems. First one is the rule limit as x approaches to a, any constant will equal to constant and k can be any constant. So an example to that would be something we actually solved in, I believe, 1.4. So if we have, let's say, limit as x approaches to 1, and then this is 4. Because we cannot plug in x anywhere, we don't have an x value, this will automatically equal to the constant. Another rule that is similar to that is limit as x approaches to a, x will equal to a. This makes sense if we solve a problem if we just plug in numbers. So let's say my a is 2 and I have my x. So if I plug in 2 for a, so x approaches to 2, and then I have x over here. If you plug in 2 for the x, this will automatically equal to 2, which is the a value. So that's what it's saying when whatever is x approaching to will equal to a if you have only x value, or if it's represented by something else but you only have one variable. Our third property is saying limit as x approaches to a, where you have two functions where the sign is positive or minus between them. You can actually distribute limits to each of these functions. So let's say we have this function. Whenever you have a 3x squared and a 4x and then we have a 1, right? Where they're separated by a plus and a minus sign. We can say this fx represents this gx represents this, and it can be more than that. But when trying to solve this, first thing you do is distributing the limits. So that would come to limit as x approaches to 2, 3x squared. And whatever is the sign between them, you put it after. So plus, and then we put limits again, limit as x approaches to 2. And then I have a 4x. And then whatever is in between, I have a minus sign. And then I put limit again. So limit as x approaches to 2, and that will be my constant 1. So when solving this, all we do is do the exact same thing we did before, plugging 2 for the x value. So I would get 2 times 2 squared is 4, 4 times 3 is 12. For here, we have 4 times 2, which is 8, so plus 8. Don't forget the signs. And for here, my function is a constant, which will equal whatever the constant is given, so it will be minus 1. So that would equal to 19 as my answer. Fourth property is basically saying if you have a function over here, so limit obviously x approaches to a, and then over here you have a function where you have a constant in front of your function. Whenever you have a case like that, you can actually take out the constant outside of the limit and put it front, so you don't have to deal with it and make a huge function with the constant and multiplying them all. Instead, you can solve for the limit itself first and then deal with the constant later. So one example we actually did previously was when we distributed our function limit as x approaches to 2, and then we had 3x squared. This is when we distributed it. Let me fix the 2. Yeah. So here you can see my function is actually x squared. And this here is a constant. What I could have done, but because this is a small function, you can just straightly plug it in. But when it gets big, this property is really useful, where I can actually take the constant out and put it over here, and I can be saying 3 limit x approaches to 2, and then I have x squared. So now I can solve for the function itself first. So plugging 2 over here would give me 4. So now I'm left with 3 times 4, where that would equal to 12, and that would be your answer. This property is similar to the one we did with two different functions and a plus or minus. The only different thing is, instead of having plus or minus in between them, we have the times sign, which is not visible, but it's times. So you have two different functions where they're times by each other, and then you have limit as x approaches to a. You can again distribute the limits into these functions and then multiply them later. So if we use the same numbers we used with the previous example, let's say my x approaches to 2 again, and then I have over here 3x squared times 4x. Now I can distribute the limits instead of solving this at once. So limit as x approaches to 2, and then I have 3x squared over here, and then that would be times limit x approaches to 2, and then I have 4x. Again, all I need to do is plug in 2 for each, so that would give me 12 times 8, which would give me 96. This one you guys will encounter it a lot. So if you have a case where a function is divided by another function and it's for limits, you can distribute limits to each of these functions again and solve it for numerator with limits and solve it for denominator, and then doing it by dividing the numbers, usually if it comes up to a number, and provided that your limit as x approaches to a gx cannot be 0, or else it's going to be undefined. So let's say, as an example, I have this function. I can distribute it to the numerator and a denominator, which I did over here, and I can either apply another property, which is not needed because it's a very small number I'm dealing with. So I'm going to go ahead and plug in -1 for my x value. When I do that, I get this. So from here, I can say -1 times squared is just going to be 1. -5 times -1 would turn into +5. And then I have a +2 over there, divided by negative times to the power of 3 is just going to be -1 times 2 would give me -2. Over here I have 3 and a -1, so that would give me -3, and then I have a +1. Now I ended up with 8 over -4, which would give me -2, and that would be my last answer. Last property is saying if you have any function to the power of n, right, where the n is any rational number, you can actually plug in limit into the function without dealing with the superscript. So I'll just solve a problem and it will make it easier. This is the example given on your textbook. So this actually represents limits as x approaches to 5, where I have a function x squared over x minus 1. This is my function, where it is power to 1 over 2. So my superscript is 1 over 2 because it's in roots. So what I can do is bring in this limit to my function without dealing with the roots. So I'm just going to go ahead and put that in. So that would be limit as x approaches to 5, and then I have my function x squared over x minus 1, 1 over 2. And here I can actually use my other property where I can distribute limit to the numerator and the denominator and solve it from there. So if I do that, I will get limit as x approaches to 5, and don't forget it's in a bracket, x squared over limits as x approaches to 5, and then I have an x minus 1, where all over 1 over 2. And if I plug in 5 for my x values, I would get 5 squared and a 5 minus 1. So if I do that, my number would be 25 over 4. So now you can convert it back to root if it's easier for you. So this technically means root 25 over root 4, which would give you 5 over 2. So you will not always encounter that direct substitution works every single time. So you're going to see cases where direct substitution doesn't work, and you encounter an indeterminate form, what we call where your denominator and numerator is 0. So if we look at this example, what I mean by direct substitution doesn't work is if I actually try and go ahead plugging 3 for numerator and denominator, I would get over here 9 minus 9 and a 3 minus 3 over here, which would give me 0 over 0, which is exactly what they're talking about over here, the indeterminate form. So in order to get rid of this indeterminate form, first thing I'm thinking is, in order to get rid of it, actually, I need to cancel x minus 3, because whatever I do down there is going to equal 0, because anyways we have to plug in 3 at some point into my function. So the next step is going to be the simplifying the function by factoring and reducing to see if the limit of the reduced form can be evaluated. So if we do that, I can actually factor the numerator. So I'm going to go ahead and say the top is actually x plus 1 and an x minus 3, and then over x minus 3. And like I said, I was trying to cancel the denominator, which I found that in the denominator I can actually have x minus 3. So only thing I'm going to do is cancel these out. So don't forget there's also a limit over here, so limit as x approaches to 3. So what I'm left with is limit as x approaches to 3 and an x plus 1. So now if I plug in 3, I'm going to get 3 plus 1, which is 4. And now I got rid of that indeterminate form. So let's try to solve this problem and see if indeterminate form plays out. So what I do whenever I see a problem is try direct substitution first and see what you get, because if direct substitution works, you don't have to deal with it, but if it doesn't work, then you know the direct substitution doesn't work. So if I plug in 0 for my function, I would get root 0 plus 1 and a minus 1 over here over 0. I see that that comes out as 1 minus 1 and a 0, and then I see I get 0 over 0, which is an indeterminate form. So now I know I need to change it up in order to actually solve the problem. So what I can do is actually rationalize the numerator, which will change the denominator, because what we're trying to do is whatever we do, even if we just change the numerator, denominator, whenever it's at some point I'm going to plug in 0, and when I do, denominator is going to be 0, which is undefined. I don't want that. So what I'm going to do is change up the denominator somehow that I get a number instead of undefined or an indeterminate form. So if I actually rationalize this, I would get the root comes out. So if we think this times this, the root comes out. So I have x plus 1. And now I'm going to do root x plus 1 times plus 1. And if we do this also, which is the same thing but a negative version, they will cancel out anyways. So I'm not going to put that. And the last version is negative 1 times plus 1, which would give me negative 1 over here over x times root x plus 1 and then plus 1. I'll just put those together. So root x plus 1 and a plus 1. And also don't forget over here, whenever you write a function again, you have to put the limit. So x approaches to 0. So now here I see I have the plus 1 and a minus 1, so they cancel out. So I ended up with limit as x approaches to 0. I have x over x root x plus 1 and a plus 1. Now I see I have x over here and x over here, which I can cancel them out by dividing it by x. So like x divided by x is just 1. So I ended up with limit as x approaches to 0, where I have 1 over here because we divided it, and then I have root x plus 1 and a plus 1. So now I see that I actually changed the denominator like I wanted to. I don't have only x now, which means that my denominator is not 0 anymore, which means that my function is not undefined. So from here I can actually plug in 0. So if I do that, I would get 1 over root 0 plus 1 and a plus 1, which would come to 1 over 1 plus 1, and then my answer would be 1 over 2. So in this question, I'm going to show you guys another way to solve indeterminate forms. So previously what we did was we had an indeterminate form, which was similar to this, where we had x in our denominator and x approaches to 0 again. So we used by rationalizing the numerator. But in this case, it's going to be super annoying to do that, and it's going to be a little harder. So I'm going to show you another way, which we call the U substitution. So I start by, for every single question, direct substitution to see if it is actually indeterminate form. And I found that if I plug in 0, it is actually 0 over 0, which it is in fact indeterminate form. When trying out the U substitution, what we are trying to eliminate is basically the annoying factor. What makes it harder for me to solve, what makes it harder to, let's say, why I didn't use the rationalizing the numerator. The only thing different over here is this factor. So what I can do is actually say, okay, let the letter U, it can be any letter, but we usually use U, let the letter U represent x plus 8 to the power of 1 over 3. And I'm just gonna plug in that U in the place of x plus 8 1 over 3 in the limit. When solving, we're gonna solve for U, because when we plug in U, then we have to solve for U, and I'm not gonna use any x, because if you have a U and an x, they will never cancel out. What we're trying to do in the first place is cancel those out. So we're going to change this factor into U. So if I equal U and plug that in, I'm going to get U minus 2. I realize I have an x over here, which I'm trying to get rid of. So what can I plug in the place of x to make it into U? What I can do over here, I realize I actually have an x, and I can solve for that x to write it in the U form. So I'm going to multiply each side by to the power of 3, and then I would get U cubed equals to x plus 8, because these would just cancel out to 1. And here I can send the plus 8 to the other side to get x equals U cubed minus 8. And I realize I can actually plug that in for my denominator now. So I have U cubed minus 8. And I need to write limits. But what I realize is that x approaches to 0. But since I'm solving for U, my U needs to be approaching to something. So what is that something? If you actually see from the numerator, we found that it's U minus 2. So you can basically say U, if U equal to 0, it's basically U equals to 2. So I can say U approaches to 2. And if you solve for the denominator as well, it's going to come up to be, if you do root to do 3 and do that, it will come to 2 as well. So we're going to approach it to 2. So what I'm going to do is actually solve for the denominator first. So factor it out and simplify it for to cancel out U minus 2, because that's the only way we can approach this. So if I simplify it, I see that I can actually take out U minus 2, and I would end up with U squared plus 2U plus 4. And what I can do is just divide these by U minus 2, and I will end up with limit as U approaches to 2, and I have 1 over u squared plus 2u and a plus 4. And I'm gonna just plug in 2 for the value of u, because now I realize it's not going to be 0 anymore, because when I looked at the numerator, if I plugged in 2 for here, I would have ended up with 0, which I do not want. That's why we wanted to cancel out in the first place. So from here, I'm going to end up with 1 over 4 plus 4 and a plus 4, which is going to be 12. So 1 over 12 would be my answer. For this question, it wants us to evaluate the limit as x approaches to 2 with an absolute value of x minus 2 over x minus 2, and then it wants us to illustrate with a graph. So for these ones, whenever you encounter an absolute value, which it is in fact an indeterminate form, so if I plug in 2 with direct substitution, I would get 0 over 0, which is an indeterminate form, which is visible from here, so I'm not going to write it. But what we do is use a piecewise function and then solve it from one-sided limits to see if it actually exists or not. So that's what we can evaluate. If it exists, we can find a number. If it doesn't exist, we're just going to say it doesn't exist. Because the limit is approaching to 2, what I'm going to do is separate the graph into 2, because I have 2 functions anyway, so I can I can make into 2 functions. So 1, 4 coming from the right side, which will be positive, so bigger than 2, and 1 coming from the negative side, so less than 2, and make that negative. So I'll just show you what I mean by that. So if we start from the right side, I'm going to put the positive version of the absolute value. So I'm going to put x minus 2, so I took it out of the absolute value, saying this is the positive version of it, and then over x minus 2, where I'm going to say this comes from the right side. So I'm going to say if x is bigger than 2. So if x is bigger than 2, meaning if 2 is over here, it comes from the right side. So that's what we do, bigger than 2. For the left side, I'm going to say this is coming from the left side, so what we do is put the negative version of the absolute value. So I'm going to put negative and then put the same exact bracket, x minus 2, and then I'm going to do over x minus 2, and I'm going to say if x is less than 2, which means it's going to be coming from this way when it's less than 2. So if I actually try to solve these, I realize that I can actually cancel these out by dividing x minus 2. So if I divide each side by x minus 2, I will end up with 1. So actually, I found that my solution is 1 if x is bigger than 2, aka if it's coming from the right side. And I realize I can do the same exact thing for the second one, but I realize I will end up with negative 1 because I have the negative in front of it, and that is if it's coming from the left side, aka if it is less than 2. So if I put it onto a graph, I realize that when it's coming from the right side, my solution is 1, but it does not include 2, so I put a circle that is not filled, and it's going towards the right side, and the solution, the y value is going to be 1. And same thing for the other one, my solution is negative 1, and it's less than 2, so not including 2, but less than 2 would go towards the left side, and the y value negative 1. Now I'm going to go ahead and do the one-sided limits. So one of them coming from the left side, so left-sided limit, that would be negative 1, because I already found the solution right over here. All I need to do is just plug in negative 1 for that, and because it is a constant, it will end up being negative 1. Same thing for the right side. I found my right side to be this function, which is 1. That's why it's kind of important to kind of visualize it on graph 2, which I found to be 1 over here. What I realized, if you guys remember from the previous lecture, is if these are the same values, the limit exists. if these are not the same values, the limit does not exist. So therefore my solution would be the limit does not exist. So that will be my solution.